haven't done that, so we will do it once we will there. Right. Today is we will working on the impact and collisions. So there are a couple of what you can say, couple of formulas related to that, couple of theories related to that, and we will see how it goes. Okay. So I'm sharing my screen and okay. So let's do one thing. Today's date is 11. Date is 11 October 2025. We'll do some momentum and impulse. Okay. Let's see. So momentum is what? Moment is given as P equals mv, right? Where m is mass in grams or kilograms, and v is the velocity, right? Meter per second, right? As we will learn about torque and equilibrium, so those will be same applied here too, and it will say that momentum momentum is always conserved isolated systems in isolated systems. So yeah, so what are isolated systems? And it will always conserve. That means if some event happen, right? So for example, if two balls are colliding with each other, right? So once we have put the force and given them the direction, just before the collision, we haven't influenced with other forces, right? So the collision happened. So the collision is happened in an isolated system. There is no further forces applied on it, on both the bodies, right? So in that kind of thing, momentum will always be concerned. That means the total momentum before total moment yes, total momentum before will equal be to the total momentum after, right? So that means if we have P before, it will equals to P after, right? All right. So this is the first concept, and the second concept is the impulse, What is impulse? Impulse is force acting over time, right? And how we are going to calculate it? So once we are saying that over time, similarly is the velocity, that if one is moving over time, right? So we will say that okay, in 5 seconds, the object of the car moved like 5 meters. So what will be the velocity? It will be like five over time, right? Similarly, if a force is acting over time, right? So that is called impulse. That means this is impulse according to the definition. Or we can say that now this is another formula for force is equals to momentum, right? Change in the momentum over change in the time, right? So this is what, sorry, this is what change in momentum, momentum over change in time, right? And this is what equivalent to when we say rate of change of momentum. Rate of, it is the same as if I say rate of change of momentum, right? So that is force, applied force, we can say. Okay. All right. So these two will eventually lead us to further questions, which will we see now. Okay. So F is equals to change in momentum over change in time. We should also remember the conservation law of momentum. What is before, what is after, right? And what is momentum itself is the product of mass and the speed or the velocity. Okay. So, and where we explicitly are using the examples, we will see uh, airbags, airbags, crumble zone, crumple zone, right? Or trampolines reduces injury. Trampoline reduces injury, right? Why? Because they increase the time, increase the time, increase the time of stopping, which reduces the force. Right. So if you can see here in this example or in the formula, what we have written F equals to delta P over delta time. If we increase this time, right, so the value of force will be decreased or reduced, right? So once, for example, let's say we increase that time to double it. Okay. So let's say with the same momentum, with the same momentum F, what we are seeing, oh sorry, with the same momentum P, or let's say I will say only P now, right? One impact is happened with this one, with this calculation, and now I increase or I doubled the time, right? So this is F1. At one time it is F1. The second time I double the time to stop. So with this, we can say if I, let's say if I, we just divided by both of them, F1 over F2, what we will look at, P over T times 2T over P. Okay. So this P cancel this one, T cancel with this one. So F1 is equals to 2 times of F2. Right. So even the time, so that's the ratio, we can say that how time impact, the stopping time impact the overall force which is being applied. More the time, less the force. That is how it is related as an inversely proportion to the time, right? The force which is we gain is inversely proportional to the force. Okay. I'm just saying here also I can write it down so that you can remember that. Stopping time is inversely proportion to force, right? So I can say inversely proportional to force. This is all, this is true, and this is also true. Okay, it's one and the same thing. All right. And now let's see what's next. These are the, okay, now let's do some questions which has been asked previously related to centripetal force and collision colliding. Okay, so I will take one example. Springs, we haven't done it yet, and that is the second example too. Okay, so there is one common question which had been asked in 2024 and 2000. So two questions actually. The same question 2024 has been asked like multiple times. 2024. This two together and move it to before collision. Okay. Yeah. So there are like collision questions has been asked previously. So let's focus on that and see if we are able to do that. Okay. So that will be okay. So let me check once again that if I have any further questions. Oh no. Okay. That's nice. So that's exam question one, which it is came in 2024. Question one, B and C. Right. So what does it saying? The B part is a 10 kg dog runs in a circle in a circle at 0.87 meter per second, right? The centripetal force, the centripetal force is 15 Newton. We need to find the circle, need to find the radius of the circle. Okay. And the second question, the C part is the dog collides with the owner, let's say Juno, who cushions the stop in 2 seconds, right? Of instead of 1 second or uh, 0.1 second, right? Explain why cushioning reduce reduces the force. Okay, so this is the question. So first one is the direct one, where it says, let's do the first one. So the B part says that the centripetal force, right? It's given. So what's given? FC, centripetal force, 15 Newton. Then mass of the dog is 10 kg. Sorry. Then we have um, speed, which is 0.87 meter per second. We need to know the radius equals to what, right? So it's simple. We know what is centripetal force. Fc is equal to mv square r. Now we have to change the subject and look for the r. So that means r equals mv square over fc. Got it? Any confusion? Let's say this is done by like the direct step, because this is denominator, r is denominator on the other side. So if it goes up to the left hand side, it becomes the denominator, and fc becomes the denominator. Yes, we can, we can do that. So this is a simple rule, like if a over b, o is over c over d, right? So I can write d over b. Oh, sorry. I can write d over b is equals to c over a. And I also write uh, d over c is equals to b over a. Right? So in this case, what is happening? We just uh, reciprocate that thing. Right? So this is d over c becomes b over a. Right? Here. For all the equations where we can see that this is happening or not, or the one that you have remembered, that how we can get how we can put r to this side. Let's do one thing. Let's move, uh, so because r, let's say So that's the easiest one that you can remember, right? And if we let it go, then we will say that m, i'm just changing the I'm just changing the directions, okay, equals fc. And then now if I uh, okay, let's do one thing. As you know that we can multiply r on the both the side, right? So r multiply by fc is equals to r multiply by mv square over r. So this will cross up, right? And this will lead us rfc is equals to mv square, right? Now divide both side by fc, right? That makes sense. Which one? Yes, yes, yes. So if we want to change, we can say so t equals v over a. When? So if v equals a times t, is that so? Yes, yes, yes. So no, no. So what I was doing previously is that I was making you understand that how this rearrangement is working. Ah, okay. so so either way, if you can do like this, like that will be good. Otherwise these are the direct ways that we can move the terms on left hand side and right hand side. Okay. Sure, sure, sure. Okay, no worries. Now forgot about that thing. We will do this way. Okay. All right, that's nice. Okay, now we came to the r thing. That means now we have to just put the values. So r equals m is weight is 10 times 0.87 square over fc is 15, right? So this will gives us 7.57 over 15, which will gives us zero point 0.5 meter. So the radius in for the circle is zero point 0.5 meter, right? Now, the next part was the dog collides with Zuno, who cushions the stop in 2 seconds instead of 1 second, right? So, what we are doing is, let's say the C part. First, we know for the collisions, we will do the momentum and impulse formula. We will using momentum and impulse formula. Okay. Okay. So, uh, impulse formula says F multiply by T is the change in momentum. Okay. So momentum before. Now we are going to calculate because there is a collision. So we first want to know what was the momentum before. Okay. So momentum before. That's the same thing. So that's what I'm saying. F equals. So this is the formula for the force. But when we are saying impulse, impulse means force is applied over time, right? So that's why we are taking this time part like this, right? And sorry, we can remember this one. And if it is asking force, we can just let the double delta t to come to the this side. And that's similar thing that we are dividing delta t from the both the side, right? Yeah. Okay. So before the momentum or before momentum, delta P is equals to mv. We have m that is 10, the v that is 0.87, which will gives us 8.7 kg meter per second. So that's the momentum before. Now, now there are two conditions, right? First one here. Now, the first one is if stopped in 2 seconds, what will happen? What will be the force? Force is delta P over delta T, right? What is the delta P that we have calculated? 8.7. And what is the delta T? 4.35, right? Sorry. My mistake. I just got distracted. So delta T is 2 seconds, and this will gives us 4.35 Newton. Okay. So this is the force if stopped in 2 seconds. Now they are saying if stopped in zero point 0.1 second, what will happen? Right? Yeah. But the time got changed this time. So delta P over delta T, which will gives us 8.7 over zero point 0.1, which is giving 87. 87, is it 87? 87. Yeah. No, this is about the collisions. That will be comes in springs, right? Okay. Now see, if it stops in zero point 0.1 second, the force applied is 87 newtons, right? But if the stopped in 2 seconds, the force reduces to 4.35 seconds. Therefore, what we the question is that the question asked is why cushioning reduces the force? Cushioning reduces increase the time because cushioning increased the time time after. Yeah. So before we have delta p, right, as 8.7, but to check the force, Once we put this, for example, see an example that this is a straight wall, right? And this is a car which we want to impact here. Okay. So without the cushioning, what is happening is it will hit directly, right? But if we put a cushion over here, if we put the cushion, if we put cushion, so that will increase the time. The car has to go through with this first and then hit the wall. So that, yeah, no, no. I'm saying that first we have calculated the momentum before the impact, right? And then we are comparing between the time that it takes, right? For the so once the collision happened with the cushion, and the second one is without the cushion, right? So the force which is we are calculating is about the after the collision. Okay. So if is collide in 2 seconds, the force is 4.35 Newton. But if it collide, or at least it stopped with the cushion or without the cushion with zero point 0.1 second, the force is 87 Newton. So you can imagine that the impact, what, how hard it will hit without the cushion, right? So that's the way. So that's why cushioning increase the impact time. That's why we use like airbags, or in fact sometimes it says that the longer the car bonnet is, the less we have injuries for the drivers, because it gives some time to collide, right? Yeah. Okay, so this one is there. We had another question. Impulse collision with wall. That's the interesting one. I need to leave now, but okay. We will continue on Monday then. Are you free tomorrow? Let's say the same, two between 2 and 3. I haven't sent it. Oh my god. Let's do it straight away then. Let me remember first before we shoot it down. Okay, save. Mm, Study. Mhm. Saved. Oh yes, this one, right? The body diagram. Yeah. Okay. Okay, and then come to here, box, compose, yes, notes, attachment. Okay, okay. Tomorrow we will complete this part, and we will start the work energy force part, right? Equilibrium. Uh, Okay, cool. Thank you so much. Bye. Have a nice day.